This video will address a special type of waves. They are the sound waves. Okay, we did all the other kind of waves. We did waves in on a string. We'll do a wave in a column of air. We talked about the harmonics, but this is sound waves. A sound wave is a longitudinal wave. It's basically a pressure wave where you have a bunch of compressions and rarefactions, and they generate a wave. And when these pressure waves reach your eardrum, your ear sends a signal to your brain, and your brain will be able to interpret this sound. And it's also a mechanical wave. And I think we did the proof to this in a demonstration in class where we put a buzzer inside a container, and we suck the air out of the container, or most of the air. The sound intensity kind of diminished. Okay? So just remember that it's a longitudinal wave because the air compresses and refracts, has a rarefaction in this direction here. So the wave compressions are traveling in the direction of the wave, or the material, the air is traveling in the direction of the wave. And it's also mechanical because it needs a medium. Without a medium, you won't hear anything. Now, humans can hear from 20 hertz to 20,000 hertz. Okay? These are just definitions you have to know. Frequencies below 20 are called infrasonic, and anything above 20,000 is ultrasonic. So we can only hear between these two ranges. We'll do a demonstration in class. We'll play some different frequencies, and some of them we can hear, some of them we cannot. And as you get older, this range kind of like shrinks. So you're not going to be able to hear the extremes. All right. Sound or sound waves will follow the same formulas as any other wave. So speed is distance over time. Speed is also wavelength times frequency. But there is another formula for the speed of sound only in air. And that formula is 331.5 plus 0.6 additional degrees, meters per second for every degree Celsius. So this T here is not tension, is not period, that's temperature in Celsius. Okay. So that should help you do the math. So let's see if we can try this. Calculate the length of the sound wave, so basically the wavelength, by a tuning fork, 250 hertz at room temperature. Room temperature usually we say somewhere between 20 and 25 degrees. So at 20 degrees, let's say, the speed is going to be 331.5 plus 0.6 times 20. So that should be about 343.5. So if you are not given the temperature, and if the wave is traveling in air, if it's a sound wave, then you would just say that the speed of sound is about 343 meters per second. Now we just set this equal to lambda times the frequency, and the frequency is 250 hertz, and you can divide and you can get your wavelength. All right, let's go back here. Okay. The speed of sound in metals, okay, is greater than the speed of sound in liquids. It's greater than the speed of sound in gases, right? What else do I have to talk about here? And that's really it for this video. I mean, it's very short. You can do the problems. These should be pretty straightforward. The other thing you have to remember is any sound wave that's traveling in air at the same temperature will have the same speed. So it doesn't matter what the frequency is, because I think we talked about this in the past, that the speed of any wave does not depend on frequency, does not depend on amplitude. You did this in the lab. And if it's in the same medium, it's got to stay, it's the same for all frequencies. Unless the medium changes, unless the temperature changes, for instance, in this case. Okay? That's a pretty short video. See you later.